So we will still learn something from it. Okay? I hope you also learned something from it, as much as I did. Okay, we're going to continue with frequency response analysis. My belief is a lot of you have seen this before in your electrical circuits class. Even so, I'm going to take my time going through the process of explaining all of these things. Okay? Regardless of where you've seen it before. Alright, so frequency response analysis. And we are learning this in tandem with electrical systems, because this is the right place for it, as you will see as we solve some problems. Before I go into the details of today's lecture, which will follow up on what we did last time, just a few brief words on why we need to do these things. Okay? So we've seen time domain analysis. Okay, so time domain or time response analysis. In time domain analysis, where we studied first order systems, we studied second order systems, we studied a whole host of inputs, a ramp response, a step response, a free response, impulse response, and so on. What we do is we look at the magnitude of the system response as a function of time. Okay, so here system response as a function of time. This is very nice for a class of problems. Okay? For example, if you're designing a spring mass damper system, you would like to know the extent of the magnitude of the oscillations of the mass as a function of time, then the time domain analysis is the best approach. Okay? But for certain other types of problems, the problems that we're going to be talking about, frequency response analysis or frequency domain analysis, I'm just going to put an arrow here, we study the magnitude of the system response as a function of the input frequency. Okay, so this study the system response as a function of input. There are several words and a lot of it is jargon in some sense. Input frequency is called carrier frequency. Carrier frequency is also called as excitation frequency. Okay, so this is input or carrier or excitation frequency. And this kind of an approach is more or less valid for categories of problems that are subjected to harmonic inputs. Okay? So whenever you see some kind of a sinusoidal input, the best type of analysis that problem lends itself to is the frequency response analysis. Example, let's say that you're constructing a tall tower, a tall building. Okay? You will have a systems engineer as a part and parcel of developing or constructing that tower. One of the factors to consider is the frequency with which the wind hits the tower. If the tower is very tall, the frequency at which the wind force hits the tower is going to make the tower structure oscillate. The oscillations are imperceptible, of course, which is why we can still live there, and that's our job. But it might perhaps happen that the excitation frequency of the wind is going to match the natural frequency of the tower. When that happens, you come across a phenomenon called resonance, which we're going to talk about in the next lecture. When things start happening in resonance, the magnitude of the system response blows up. It becomes very, very large if there is no damping present. And as a result, this is going to lend itself to structural instability. The tower can collapse. A lot of bad things happen when that happens. So that is from the point of view of a mechanical engineer. From the point of view of electrical systems design, if you want to design filters, low-pass filters, band-pass filters, and so on, frequency domain analysis or frequency response analysis is what you typically have to go through. Okay? And we're going to go through some of that in this particular lecture. Alright, so that's the motivation for frequency response analysis. Now I want to revisit our claim of the day from last class. Don't need to read all of these. We had a source, sinusoidal source, Vs of t, and then our aim was in this situation to capture the dynamic relationship between the voltage across the capacitor terminals. Excuse me. Voltage drop across the capacitor terminals, and we came up with the relationship, and we drew this very nice block diagram, right? We have a linear, stable system. Right, the time frequency is a positive number. If I have a harmonic input onto the system, Vs a sine omega t. People in the back, can you see my writing? Okay, so input was Vs is a sine omega t. The output, I'm going to write it out. We are looking at the steady state output. Okay, steady state behavior. Was Vc was a by square root 1 plus tau square omega square sine of omega t plus phi, where phi was minus tan inverse of tau times omega, and tau was r times c. Okay, this was the time constant. So the huge moral of the day story thing was, if I have a purely harmonic input to the system, a purely oscillatory input to the system, the long-term behavior of the system is also purely oscillating or purely harmonic. Okay, this was the big claim of the day. And this is true for any kind of a linear and stable system. The keyword is linear and stable. Okay. Now, we wrote the system transfer function, so T of S. This is the transfer function block diagram, right? So T of S, we wrote it as the following. One by 1 plus tau times S, and we said that if we magically substitute S is equal to J times omega, then we get J tau omega plus 1 in the denominator, 1 in the numerator, and we said that this is a complex number, right? It's a ratio of a complex number with a zero imaginary part and a complex number with some non-zero imaginary part. It's still a complex number. And we said that, okay, if I take the magnitude of this complex number, what do I get? I get the portion that is seen here, 1 by 1 plus square root of tau square omega square. And if we look at the face of the complex number, this ends up being tan inverse of that. And as a consequence, what we figured out is, if I know the transfer function of the system, and if the system is subjected to a purely harmonic input, I do not need to solve for the system response. I can obtain the gamut of the system response by knowing only the transfer function. Right? And so I can now write the system response, Vc, as A magnitude sine omega t plus the phase. Right? So this was the system response. And I want to see if there are any questions so far. I know I went through the last part a little quickly last time because I have a feeling you've come across complex numbers. Yes, question?
I wanted to know whether this only applies to the RC circuit or...
Oh, it applies to any kind of a system with a harmonic input. Absolutely, absolutely. We are going to look at other systems as well. Second order systems, spring mass damper systems. We are going to look at them too. Okay? This is true for all kinds of systems. That is the beauty of this thing. If you know the transfer function, you are done. Just move on. That's about it. Okay? And this magnitude of the transfer function itself in the omega domain has a special name. It's called as the frequency response function. So T is called as the frequency response function. My shorthand. And the one thing I want to point out, the magnitude of the FRF, which is this guy, is, in our case, okay, is 1 plus tau square omega square. Look at this now. I will take the magnitude of the output, which is Vc of t. What's the magnitude of the output? It's A divided by all of those terms, right? So that's A by I will take the magnitude of the input. What's the magnitude of the input? It's capital A. And what do you see here? The magnitude of the frequency response function is nothing but the magnitude of the output divided by the magnitude of the input. And this term is called as the total system gain. Okay, or just a system gain, or some people just call it only the gain. Okay, so I'm going to write this down here. So is magnitude of the output divided by the magnitude of the input. This is the magnitude of the frequency response function, and this is called as the system gain. So whenever somebody says system gain, magnitude of the output, magnitude of the input, and this consequentially is also the magnitude of the frequency response function. Make sense to everybody? We are going to revisit this term gain many times because you're going to see different types of gains when you go to control systems. You'll see open loop gain, you'll see DC gain, you'll see a gain factor, you'll see a gain constant. You'll also see system gain. There's only one and only system, one system gain. Okay, the system gain is magnitude of the output, magnitude of the input, which is the magnitude of the frequency response function when S is equal to J omega. Quick point that I want to make here. In reality, the Laplace variable is sigma plus J omega. If you look at that block diagram that I've drawn there, you see that the input is a purely harmonic signal. The output is a purely harmonic signal. Okay, or a harmonic function. Signal, function, everything is the same thing here. If you look at the Laplace variable itself, this term sigma is typically present to model exponential decay or exponential growth. You would have known this if you had plotted the pole zero diagrams. The term sigma, if it is a negative sigma, you would be in the left half of the S-plane, positive sigma, right half of the S-plane. Right? So this sigma term represents decay or growth. Okay, and the omega term represents the oscillatory part of the signal. And you see, for a purely harmonic signal, there is no growth or decay part. Which is why, when we are doing these frequency response analysis, we substitute S is equal to J omega, and we do not substitute S is equal to sigma plus J omega. Okay, this is because the input is purely harmonic, there is no growth, there is no decay. The output, as you can see with our own nice eyes, is also purely harmonic, there is no growth, there is no decay. Okay? So in our frequency response function, the input is pure harmonic, which implies the output is also purely harmonic, which is when you do frequency response analysis, you say that S is equal to j omega. So for the frequency response function, we say sigma is 0, so S is j times omega. This is the real physical reason. The mathematical reason is only if you put S is equal to j omega will you be able to recreate the output using the magnitude of the FRF and the phase of the FRF. Okay, the physical reasoning is there is no growth, there is no decay. Pure input, oscillatory signal, purely oscillatory output signal. Okay? So with that said, I want to see if there are any more questions before I go to the next part of our lecture, which is trying to understand how to plot frequency responses. Right? We've done it in the time domain. You solve for the system response, x versus t. How do you do it in the frequency domain is by making use of Bode plots. Okay? Questions, please? And we're going to do this for different other types of circuits as well. All right, I'm going to pull the top panel down. So what we are going to do next is, okay, how do I obtain the system response in the frequency domain? How do I visualize it? And the visualization is done using this Bode plot by Hendrik Bode in 1938-40s. Hendrik Bode got his bachelor's and master's degree in mathematics from Ohio State, and then he went to work in Bell Labs, and Bell Labs was doing good stuff, and he was instrumental in coming up with this asymptotic analysis for frequency domain problems. Okay? When Bode was working on these plots, their emphasis was on amplifier design, or mostly power electronics, and so a lot of the terminology is left over from there. Even though we are applying it to maybe spring mass damper systems or designing car suspension systems. Okay? All right. So this is around 1938. So this is Bode plots. These are a graphical representation of system response in the frequency domain. Graphical representation of system response. Frequency domain. And today I will just present this simple example, but then next class we will come back, reconstruct a more complicated example and have some rules for plotting the Bode plots. I want to set the emphasis on what we are doing today here. As most of you may be knowing, the Bode plots are a set of two plots. Okay, one is called the magnitude plot. And the phase plot. As a mechanical engineer, as a mechanical designer, the magnitude plot holds more glamour for somebody like me and for most of us. The phase plot will become more important when you perform control system analysis or when you perform electrical signal analysis. So I'm not going to focus more on the phase plot, I'm going to focus more on the magnitude plot. Okay? So what do you do in the magnitude plot? you plot the following two quantities on a log-log scale. There's a plot of 20 log to the base 10, okay, of the magnitude of the frequency response function. This is plotted as a function of omega, which is the excitation frequency of the carrier frequency. The first term has units of decibels, or dB. This is obviously radians per second, and many questions I know are there in your mind. Perhaps you know the answer to them. Why do I have this factor of 20? Why do I have to use a log scale? What is this creature decibels? And this is all plotted on a log scale, on a log-log scale. And it might look like this. And we're going to call that term 20 log 10 T of j omega as a term capital M. So call M is 20 log 10 T of j omega. And remember, what is T of j omega? The magnitude, of course, is the magnitude of the output to the magnitude of the input. Okay? Just recall our memories. Magnitude of the output, magnitude of the input. This is plotted on a log-log scale. On the x-axis, omega will be increasing by a factor of 10. An increase by a factor of 10 is called as a decade. Okay? Or change by a factor of 10. And likewise, an increase or a change by a factor of 100 is a century, and so on. Century is not as much used, but decade is more often used, and you would have come across this in circuit design. And on the y-axis, you plot M in decibels. 0, minus 20, minus 40, plus 20, plus 40, and so on. Okay, we'll see actual examples of this. So this is what you do in a magnitude plot. And what are we trying to do? We are trying to find out, okay, how is the magnitude of the system response changing as a function of the carrier frequency? That's essentially what this plot says. How much is the magnitude of the system response on this odd scale changing as I increase my carrier frequency by a decade? Okay? So, questions that occur to me, and which are not very obvious to me at all, is first of all, what is this pesky factor of 20 doing here? The second thing is, why on earth is there a log? Why not plot it on a linear scale? Okay? So those are the obvious questions to me, and perhaps other questions as well. I'm going to answer them now. There will be a more in-depth answer in my lecture notes on the difference between a log scale and a linear scale, and I believe you may have come across it. It's not very obvious at all, by the way. So please refer to that for more details. But let me get rid of the easy piece first. Why do we use a log scale? Many reasons. First reason, the simplest reason, is you see on the x-axis, I can sample a wide range of the frequencies. I can go from 0.01, I can go from 0.1, I can go all the way to 10 to the power 5, 10 to the power 8 radians per second. So I can sample a wide range of frequencies and understand how the system responds. That's the first one. Okay? Second one, I love the log scale because you take a curve in a linear scale, it becomes a straight line in a log scale. I take a third order curve in a linear scale, it becomes a straight line in a log scale with a different slope. So the only thing that changes in the log scale is the slope. But other than that, everything else is straight. It's linear. So that's another advantage of using the log scale. Okay. Third reason is the nicest reason that I can imagine, and we owe a debt of gratitude to two gentlemen, Weber and Fechner. Ernst Weber and Gustav Fechner, 1800s, 1840s, 1700s, 1800s time frame. They came up with this startling observation that the scale that is most natural to human perception is the log scale. And they performed a multitude of experiments, and then they came up with this very nice equation. It says that human perception what is perception? Sight, sound, touch, right? Is directly proportional to the logarithm of the stimulus that awakens these perceptions. Okay? It is proportional to the log and obviously Bode, being the interesting person he is, made use of this observation and figured out, okay, this is most natural to the human sense. It also takes something that is a curve, makes it into a straight line, and I can also sample over a very wide range of frequencies, so I'm going to use a log scale when I plot the Bode plots. Okay, so this was the reason for the log scale to be present. Does this make sense to everybody? Okay, interesting and not very obvious at all, in my opinion at least. The second reason is what's that fellow of 20 doing there? For that, we start our journey by describing what is meant by the power gain of a system. Okay, so when Bode was looking at these kinds of situations, they were more interested in power gain of a system. Was given as the following: log 10. We know why the log scale was used by Bode. Okay? But the power gain was defined as log 10, magnitude of the output power divided by magnitude of the input power, and this was measured in units of bells. Named after you know who. Alexander Graham Bell. He is the fellow who made all our lives miserable by discovering a telephone and killed letter writing and all these things that my grandmother used to say. Okay? So Alexander Graham Bell, named after Bell. What does this mean? This means the following. Okay? A power gain of 10 means that it's equal to 1 bell. Do you see that? A power gain of 10, which means that if the output is 10 times greater than the input power, then it means that the power gain is 1 bell. So this is like saying, okay, 1 ME 3260 lecture is equal to 1 Satya. So 10 Satyas is 10 3260 lectures or 10 years of your life wasted, something like that. Okay? So that's exactly what it means. It's a unit to measure power gain. That's all it is. But then people found out this bell is a very large unit. Okay, so for example, if I say P output is 10 times the input, then the gain is 1 bell. They wanted to reduce the intensity of this and say that, okay, instead of calling it as bells, let's call it as decibels. Decibel is 1/10 of a bell. Okay, so decibels is 1/10 of a bell, and so they rearranged this power gain equation and they said, okay, Bode said, okay, power gain, if I'm going to now measure it in decibels, which is making it slightly a smaller number, then this is going to be 10 log 10 in decibels. So you see where we started? We started off by saying, okay, this was done to understand how amplifiers work. the gain of amplifiers and so on. So amplifier gain is defined as log 10 of the output to the input. The log scale is used because it's most natural to us, and this is measured in units of bells. Somebody did not like bell, and they said, okay, bring on decibel. Okay. So we brought in the decibel, and immediately you see a factor of 10 coming into play. How do we make it 20? Here is how we do it. If you look at power electronics, right? Power is what? What's power in electrical systems? How do you measure power? What's the equation? Yes? Voltage times current. Fantastic. If I use Ohm's law, current is proportional to voltage, which means that power is proportional to voltage square. And so you see, I'm not interested in power gain. What am I interested in? You see, my output is a voltage, my input is a voltage. So I'm going to take the power and replace it by the voltages. So here is what happens. This is now 10 log 10. Output power is voltage output square. And same story here. And if I have the square, and if I have the log 10, then I can just say log 10 of a quantity square is 2 times log 10 of the same quantity. And so I can take the factor of 2 outside, and I can say this is now 20 log 10 of the output to the input. Apologies for writing it this low here. Hopefully everybody can see. People in the back, if you want to. Okay, this is the situation, and so this is why we are using 20 log of that quantity, and you obviously know that T of j omega is magnitude of the output. And so we substitute it here. Okay, so this is the basis for that entire scenario of using logs and 20s and 10s and so on. And this is going to be measured in decibels. Okay. I want to see if there are any questions. Once again, this was invented for a different purpose, but its generality is so nice that you can use it for any kind of an application where you have a harmonic input. I'm going to pull this down. So that's one thing, and so we're going to make use of this to plot the frequency response for our system. Okay, so let's go back to our system. How do you plot the magnitude plots? We make use of what is called as asymptotic analysis. Okay? So for us, T of j omega was 1 by 1 plus tau times s, we know this. And so magnitude, this is the frequency response function. And so magnitude 1 by square root 1 plus tau square omega square. Okay? I want to plot the Bode magnitude plot. How do I do this? Here is what we do. So M is 20 log 10 T of j omega. This I am assuming is not anything new to most of you, but maybe the basis is slightly newer. So this is 20 log 10 of 1 1 plus tau square omega square. I do not like to use it this way. Okay, here is what I do. This is typically what is done. Okay, what we do is this. We first of all rewrite, and this is of course j times tau omega. Here is what we do. We start off by rewriting the transfer function in a nicer manner. And this is just to make the process of drawing the figure easy. That's all it is. There is nothing special about this. So this I read as 1 by 1 plus S by 1 by tau. Okay, once again, there is nothing that is physics based in this approach. It is just that it makes it easier to draw the Bode plot. Okay, so I first write it that way, and then write the frequency response function. Then we write T of j omega by substituting S is equal to j omega. So this is now 1 by 1 plus j omega by 1 by tau. I won't be writing any of these steps from the next time. Okay, so this is the only time I'm going to go through the details. Then we take the magnitude. Is 1, magnitude of the numerator is 1, magnitude of the denominator is the sum of the squares of the real and the imaginary part, square root of that. So 1 plus omega by 1 by tau whole square. And then I write my gain term. Okay, this capital M, this is the system gain in the Bode plot. So then we say M is 20 log 10 of magnitude of T of j omega, which is this big guy substituted here. 1 plus omega by 1 by tau square root. Nice thing about log scales is if I have any divisions, they become subtractions. If I have any additions, they become multiplications. Yes, question?
Will it, that turn into 1 minus W over 1 over T?
Why?
Because J turns into the J.
No. So when I'm taking the magnitude of a complex number, as we said in the last class, I am squaring the real part. I am squaring just this part. That's how the magnitude of the complex number is defined. Okay? You're not squaring the J. Okay? All right. And then we make use of the fact that log A by B is log A, log B, all of them are log 10, so I'm not going to keep saying log 10 all the time. I use that, and so this becomes 20 log 10 of 1 minus 20 log 10 of square root whole square. Okay, when you take the magnitude, square of the real part plus the square of the imaginary part, square root of that. Magnitude of the numerator is 1, magnitude of the denominator, write it this way. What is the log of 1 to the base 10? It's 0. So this is gone. Instead of the square root, I'm going to take the square root out, and so that becomes 20 divided by 2. So that M is now minus 10 log 10 of 1 plus omega by 1 by tau square. And you will know why I am going to write it this way. Is because if I write it this way, you will immediately recognize something called as the corner frequency or the cutoff frequency of the system or the break frequency of the system. Okay, and that is this creature right here. We will come across this again. Okay, I'm going to define all of these things, but I just want to point out why I'm doing all this crazy stuff here. Okay. So then we plot. In MATLAB, if you want to plot Bode plot, you just say Bode, you're done. It gives you the phase plot and the magnitude plot. I am not going to use MATLAB. I'm going to make you do it by hand. You cannot use MATLAB to plot your Bode plots. Okay? This is all done only by hand. Right? How Bode wanted it to be done. In memory of Bode. Alright. So we do the asymptotic analysis. Omega is the carrier frequency, right? And so we say, okay, what happens to this gain term, this capital M term, when omega is very, very low, right? So I'm going to call that as omega is very small. What happens to the gain term? I'm going to call it as M low, because this is low frequency gain, right? This is going to be minus 10 log 10 1 plus omega by 1 by tau whole square. If omega is very, very small, what's omega square? Omega square is even smaller. And so this term goes off. And so what happens? I get minus 10 log of 1, which is 0 decibels. Okay, so M low is approximately, now this is an approximate analysis, right? This is an asymptotic analysis. So this becomes minus 10 log 10 of 1, 0 decibels. This is great news. I'm going to erase the rest of this. You obviously know what we're going to do next. We're going to look at values of omega that are very, very large. Okay? So that is called the high frequency asymptote. When omega is much greater than 1, I get M high. This is the low frequency asymptote. Okay, it's a line of some sort, an approximation. This is the high frequency asymptote. This is now minus 10 log 10 when omega is very, very large, what happens is that this term omega square becomes even larger, which means that this term of 1 is insignificant compared to that. So get rid of it. So that M high is minus 10 approximate log of omega by 1 by tau whole square. Now here is when I bring the tau to the top, I get rid of the factor of 2, and so M high becomes minus 20. Why did it become minus 20? I'm getting rid of the square, bringing it out. And then this is omega by 1 by tau is omega times tau. Am I making sense to everybody so far? So I have the high frequency asymptote, I have the low frequency asymptote. What happens when omega is equal to tau? Look at the high frequency asymptote. M high is minus 20. I'm sorry, omega is 1 by tau. Apologies. When omega is 1 by tau, it's 1 by tau times tau. Zero decibels. So when omega is equal to 1 by tau, this special value, my high frequency and low frequency asymptotes meet. Let me increase it by a decade. After you're older by 10 years, not any wiser, you decline. These senses decline, and that's exactly what happens. Tau and tau cancel off. Log of 10 is 1, so this is minus 20 decibels. As you grow even older, what do you think we should be getting? 40 decibels. And you get the idea, right? If I increase by every decade, I'm going to be dropping down by 20 decibels. And so this is where this equation occurs. And now if I plot it all out, I'm going to wait until everybody has everything before pulling the fan down. And I'm pretty sure you've come across this in your electrical systems class. Maybe the same way, maybe a different way. I don't care. Now we plot it all together. And we are not done. There are a couple more subtleties involved. So we have M low, 0 decibels, M high, minus 20, log 10 of tau times omega. And for every decade that we are increasing in frequency over the time constant, which is what I've done here, for every decade omega from 1 by tau to 10 by tau to 100 by tau, every decade produces a 20 decibel decline in the high frequency asymptote. Right? It's a decline because it's a negative sign. And every time I jump by a decade, I reduce it by 20. So that's a 20 decibel per decade drop. And so we have 10 to the power minus 2, something there, something there. This is omega. This is let's see, minus 20, 0, 20. Please label the graphs. Minus 20, minus 40, and so on and so forth. So first thing is I plot the low frequency asymptote. It's always 0 decibels. This is M low. Then on the x-axis I mark the point when omega is 1 by tau. So perhaps somewhere here, I don't know. At that particular point, the high frequency and the low frequency asymptotes meet, and the high frequency asymptote is declining by 20 decibels every decade. So this is M high. This is a slope of 20 decibels per decade. And this is the asymptotic plot, and the real plot is not going to look like this. It's going to have a slight curvature to it. If I plot it out, right, so the dotted line, which is shown in a slight curve, is the real plot. It's not a curve actually, but close enough to being one. And let's see what really happens at omega is equal to 1 by tau. So the actual frequency response function. I have a few more minutes. So M minus 10 log okay, this is the actual gain without any approximations done. When omega is 1 by tau. Minus 10 log 10. And what's that going to be? That's omega by 1 by tau, and that's going to be just 1. So that's 1 plus 1, which is minus 10 log 10 of 2, which is minus 3.04 decibels, or approximately minus 3 decibels. That's not what I want. Who cares about that number? Here is what I want to do. M, which is the power gain, as you know, is 10 log 10 right. This is a basic definition. This is where we started. This is in decibels, and then we substitute voltage, and so it becomes a square, and so it becomes 20. at omega is equal to 1 by tau, this is now, watch this, minus 10. Bring the negative sign inside this creature here, so this 2 becomes 1 by 2. So that becomes now does this make sense to everybody? Okay, I had this as negative 10, but I'm getting rid of the negative sign, bringing it inside the parenthesis here, so that becomes 1 by 2. And what do you see now? I have a log quantity equal to another log quantity, cancel the factor of 10, cancel the factor of 10, take the inverse logs, and so I get P output is equal to half of P input when omega is 1 by tau, and when this happens, this special frequency where the output power is half of the input power is called as the cutoff frequency or the corner frequency or the break frequency. This is the meaning of that term. Thank you, it's not at time. Hang on a minute. So once again, what is special about omega is equal to 1 by tau is that the output power becomes half the input power, which means there is some kind of an attenuation or a gain taking place afterwards. Okay? We don't know whether it is gain or attenuation until you look at the actual plot. And so this is called as a cutoff or corner frequency. Okay, cutoff frequency is what I would like to call it. Corner frequency is what the electrical engineers like. And essentially what happens is that this system here behaves as a low pass filter at the cutoff frequency, because when omega is less than 1 by tau, there is no gain appreciably there. The output power is the same as the input power. But as soon as I cross this corner frequency or cutoff frequency, you see that my system gain just drops down, which means all the carrier frequencies that are very high in magnitude does not cause anything to my system. They are not allowed to make any changes to my system behavior. They are not allowed to pass. It's only the low frequencies that are allowed to pass, and so this is called as a low pass filter. Okay, thank you.